Hi everybody, Physics Ninja here. Today what I want to do is look at a parallel RC circuit problem. I did a video on a similar circuit problem several years ago, except in that case my power supply was a DC power supply, so I had a constant voltage with time. In this video here we're going to switch it up a little bit. We're going to consider the case now where I have a voltage. If I plot it as a function of time here, my voltage is going to vary with time, and I'm going to give it a function, okay? It's going to vary like cos of omega t. So my goal at the end of the day is going to be to find the voltage across every element in the circuit, also find the current through each branch. So we're going to have to see how we calculate the magnitude of all of those voltages and currents, and also how are we going to calculate the phase between all of these different elements. All right, so before we get started, if you like this video, give it a thumbs up. Consider subscribing to my channel. All right, let's get started. All right, so the first thing I want to do is let's just start with some definitions. Again, what follows, we're going to assume these values here. The amplitude of the voltage over here is 70 volts. The frequency, the linear frequency, 60 hertz. R1 and R2 are 30 and 100 ohms respectively, and the value of this capacitance is 100 microfarad. Again, what we're assuming here is that we have a voltage that varies with time, and it looks something like this. V naught cos of omega t. Okay, and remember, omega is an angular frequency. It's related to that linear frequency just by 2 pi f. So again, you can get a numerical value for omega and substitute that in there. All right, the first thing you want to do whenever you've got a complicated looking circuit like this is if you're able to simplify it in any way, I think you should start by doing that. And one thing we could do is, our goal now is going to be to keep this AC supply, and then we're going to try to simplify this network of resistors and capacitors and replace all of that with just one single total impedance value. Okay, so we have to combine things that are in series and parallel in order to get to this Z total value. Okay, that's going to be the goal. So one preliminary step I could do is, well, let's start with just defining maybe an intermediate step. We have a resistor R2 that is in parallel with this capacitance. Okay, so what we want to do is maybe I'm going to define the impedance of everything here in this red dashed line. I'll call that Z1. And it's very easy afterward to calculate what Z total is. Z total is simply going to be the value R1, and that there is in series with this other value, this intermediate step called Z1. So how do you find the value Z1? Remember, Z1 now is, well, it's combining two elements that are in parallel with each other. So what we have to do is simply use the parallel rule, right? It's easy for the value of the resistance R2. However, what do you do with the value for this capacitance? Okay, and what you have to remember for the capacitance is the reactance of the capacitance is 1 over omega c. That's the definition, okay? And if you wanted to calculate an impedance, impedance of that branch with the capacitor, in this case, you have to introduce this complex variable over here, and that's it, okay? So now we have a value for the impedance of the branch with the capacitor. We have the value of the resistance R2. The way we combine both of these now to find the value of Z1 is simply use our rule for parallel impedances. So it's 1 over R2 plus 1 over Z1, 1 over the impedance of the capacitor. I'll just call it ZC. All right, now we can substitute our values in there. So we have 1 over Z1, we have 1 over R2 plus the impedance of the capacitance, when you put it in this term, simplifies to this. Okay, so now we still have to do a little bit of algebra here in order to get to Z1. What I first do is put things on a common denominator. Now this gets a little bit messy, but that's okay. I omega R2C. Okay, now we have to just take the reciprocal of each side here, so we're left with our final expression for Z1 is going to be R2 and divided by this complex number here, and that's fine, 1 plus I omega R2C. Okay, so that's our value for Z1. Well, guess what? Now this allows us to find what the value of Z total is. You simply have to substitute it into this expression right here. So the last step on this page, then, I'm going to get to this final algebraic answer over here. So it's R1 plus R2 over 1 plus I omega R2C. All right, we did quite a bit of work here, and we have this kind of messy looking expression. There's many ways to write this. At this point, I don't really care about that. I can simplify that into a real and an imaginary part. And if I was going to continue with this problem algebraically, I would probably do that. But that's a lot of extra math for me. Eventually, what we're going to do here is just substitute these numbers, and it's very easy to get the real and the imaginary part. Okay, so let's go on the next page and figure this out. All right, we're going to continue this algebraic manipulation here. What we want to do is we want to separate out the real and the imaginary part of this impedance over here. So one first step I do is I multiply and put everything on a common denominator. Okay, so I do this plus R2, and now everything is over this common denominator of 1 plus I omega R2C. All right, that's still not very kind of a friendly expression because you have imaginary terms and real terms everywhere. So we have to continue. So what we end up doing here to get rid of the complex term in the denominator is you multiply by the complex conjugate of that term. Okay, and what that looks like now is you simply swap the sign. R2C and 1 minus I omega R2C. It's the same term in the top and the bottom here. Okay, now the advantage of doing this now, when you multiply through everything, you no longer have a real and an imaginary part in the denominator. All you're left with here is 1 plus, the i's cancel out, and you're left with this term here that just ends up being squared. So that simplifies your life quite a bit. Okay, now the last part here is, again, now you have to multiply. Again, I have to be a little bit careful because this really multiplies everything here. Okay, so we're going to have to multiply that through. So the first term here is R1, and then you get a similar term here of the step we just did, right? So we have a bracket, 1 plus omega R2C squared. And then the last term here is plus R2, 1 minus I omega R2C. All right, now this might look really complicated, and it is. However, it's easier to separate out the real part and the imaginary part, okay? Because you can write this as a real part of Z total plus I multiplied by the imaginary part of Z total. All right, so let's continue with the math. So you want to group all the real terms together, right? This first term is a real term. This here is going to be a real term. The only imaginary term is going to be this last term right here. Okay, so let's go ahead and separate that out. So we have that the real part of Z total, okay, is going to be R1, 1 plus omega R2C. Remember, this term here is squared. And again, plus R2. And again, both terms are going to be over the same denominator. All right, and now the imaginary part of Z total is going to be equal. Again, there's only one imaginary part, and that's this guy. Can't forget that negative sign. And again, it's always over that same common denominator. Can't forget that either. But I get minus omega R2C divided by, again, the same term, 1 plus omega R2C squared. All right, so this is what we have now. We have our impedance. The reason that you want to do this is because it makes calculating the phase angle very, very easy if you have the real and the imaginary part just split up nicely. And in this case, it's messy, but it's still doable. Okay, now let's go ahead and substitute our values and see what we can calculate now with our more simplified circuit. All right, if you think about everything we've done now, so we've taken this complicated circuit, I've represented by something a lot simpler, except now my impedance was complex. Actually, just to simplify this notation here, I'm going to call this ZR plus I and ZI for the imaginary component, okay? My goal now is to find what is this maximum value of the current, right? The current, I simply write it as I max cosine of omega t. The voltage, now is no longer in phase with the current because we have a complex impedance. Okay, the voltage is V0 cos of omega t plus phi. Okay, and if I do this, okay, if I put this angle right here with the voltage term instead of the current, okay, I kind of like to do it. It makes kind of the math a little bit easier for me. At the end of the day, what you can find here, if I use Ohm's law, you're going to find that the maximum value of the current, again, is simply going to be the maximum voltage, V0, divided by what is the magnitude of this complex impedance. And how would you find that if it has a real and an imaginary part? Well, you simply square each component and you add them up. So you take that real part, you square it, and you take the imaginary part and you square it and you get a value. Okay? At the end, that allows you to quickly find what is the maximum value of the current flowing through this part of the circuit. And if I go back to the original circuit, that means it's the current flowing everywhere here. Also the current flowing through the resistor R1. Now, how do you find the phase angle? This phase angle, again, if you have a real and an imaginary part of this impedance, right away you can write that the tangent of this phase angle is equal to the imaginary part, the ratio of the imaginary part over the real part. Okay, so you can write that that phase angle is inverse tan of Zi over Zr. All right, what we're going to do now is let's go back and substitute in our values and see what we get here for I max and for this phase angle. And then we also need to do a little bit more work because I'm really interested in what is the current over here, what is the current in this branch, and also what is the voltage across all of these other elements. All right, we go ahead now, we substitute in some of our values. First thing we want to calculate is this omega. We tend to use this a lot. This is simply 2 pi f. 2 pi times 60 gives me something like 377. Again, that is in radians per second. Next thing I wanted to calculate was what is Z total? Z total had a real part and an imaginary part. Again, you go ahead and use kind of some software, use your calculator, be very careful, but you have all the values here for R1, R2, C. At the end, the real part, I got a value of 36.57. Again, hopefully there's no rounding error here. And then minus, I had the minus because of this guy over here, 24.78. multiplied by I. Okay, so that was the complex value of the impedance. Now, the other thing I was interested in was what is this maximum current? The maximum current was defined as the maximum voltage divided by the magnitude of Z total. So I had to go ahead now and calculate what the magnitude of this guy was. Again, just using the equation, the magnitude that I got was 44.18, and that is actually measured in ohms. Okay, so let me just highlight that value. That's an important one. You go ahead and you substitute that into my maximum current equation. I get a maximum current of 1.584 amps. Okay, and the phase angle now, the phase angle between that voltage and the current, the phase angle phi, which we had defined as tan of -1. Again, that was the ratio of the imaginary part to the real part. So that would be minus 24.78 divided by 36.57. Okay, that gave me a phase angle of minus 34.12, and I'll just write that in degrees. Okay, so these were kind of our starting point. Now, what if we were going to write down our expressions now for voltage, for current, and then we go back to our circuit and calculate the rest of our quantities? All right, so let's think about everything we've done so far, right? We've taken this, we've calculated I max, which we got our phase angle now between this voltage and the current through that branch. Now, the current in this branch has to be the current everywhere here, right? There can only be one value of the current over here. Now, what this allows you to do right away is find what is the voltage across the resistor R1 as a function of time. How would you write it? Well, Ohm's law would tell you it's the value of the resistance R1 multiplied by the current flowing through that resistance. So right away, I can write this as VR1. What is I of t? That's the current flowing through here. That's the value we just found before. That's I max. Again, there's no additional phase here. It has to be the same current flowing through R1. Okay, so this is it. So what is this amplitude here? This amplitude will be the voltage, the maximum voltage across that resistor R1. Okay, so what you can do is you can find that. We'll just call this VR1 just as the amplitude. You go ahead and substitute the values here. So we have 30 for the value of the resistance R1, and we have our value I max, which we just solved for, 1.584. This gives me a maximum value of the voltage of 47.52. Okay, so let's go ahead and highlight that value. All right, the next step now, which is going to be really important, is we need to find what is the value of the voltage right here at this point. I'm going to call this V2, right? What is this value? If I know this value of the voltage, well, I know it has to be the same voltage across the capacitor as it does with the resistor R2 because they are in parallel with each other. However, it doesn't mean that the current is going to be the same, right? Because we have different values of impedance going through each branch here. And we can also have a different phase for each individual branch for the current. Okay, so next step is going to be calculate what is the voltage here at this point, and then calculate the currents in these other branches, and then we'll be all done. All right, so how would we apply now Kirchhoff's loop rule to this circuit over here? One thing we could do is, well, again, imagine you started right here and then you added all the voltages, right? So you'd say, well, you add the voltage over here of the power supply. Now there is a voltage drop, say, across R1. Maybe I represent that by minus VR1 of t. And now there's a voltage drop, say, across R2 or across the capacitance, and I go back to where I started, right? That's called V2 of t. Okay, and then I go back to where I started, right? This is what you would call Kirchhoff's loop rule, or voltage law, actually. Let's just call it the voltage law, KVL. It's late night here. Okay, so my goal is to find V2 of t. So let's just rearrange this. How would you do this? V2 of t. Just bring it on the other side. You're left with V of t, then minus VR1 of t. Okay, here's my expression. Now what we're going to do in order to find this, now you could do kind of a lot of algebra, but we're going to represent it as a phasor diagram. I'm going to show you how to do that. Okay, V of t, you know, it's the voltage across this power supply. It's V naught cos of omega t plus phi. So the way that you represent this value right here, now V naught has a magnitude of 70. I'm going to go ahead and just draw this vector here. Okay. Let me go ahead and change colors. Let me show you what I did here. So remember, this value here is 70 volts. That's the length of this vector. That's the length right here. Now, why did I go down? This is the angle phi. Remember, my angle was negative, right? That angle that we originally found, what was it again? Let me go back on my notes here. We found that that angle phi was a minus 34.12. Let me go ahead and just write that. Phi was equal to minus 34.12 degrees. Okay, now what would I do now in terms of this equation? Well, I would take away VR1 of t. Let's go ahead and plot what VR1 of t looks like. Now notice here it has no phase factor. If something doesn't have a phase factor, what you do on a phasor diagram is you plot it simply along this axis right here, along this x-axis. Now the magnitude of this we just calculated. Now the magnitude, you have to be a little bit careful for this one, okay? So it's the value we calculated. That was, switch the colors here, that was 47.52 volts. That's the magnitude of the voltage across that resistor. And again, there was no phase factor. So what we're left with now is going to be this purple, okay? What we're left with is going to be this purple arrow. And again, if I'm just using Kirchhoff's loop rule, I have to have that the voltage across that resistor plus the voltage across this, whether you go across the capacitor or across the resistance, it has to have the same voltage across because it is in parallel, right? Both of those branches are in parallel. So this is how I would write the magnitude of this voltage. I have to find the length of this arrow. The other thing we notice is that there's also some phase angle, right? There is going to be some phase angle, and I'm going to call this angle right in here phi 2. We'll give it a different value. Okay, so that means at the end of the day that my voltage as a function of time, I have to write as some amplitude, and it's going to be cos of omega t, and then again, looks like the angle is also going to be negative, but let me just write it out like this. The math will tell us in a minute, but this is what I'm trying to solve for. How do I find this guy, and how do I find this guy? And then I'm going to know the voltage right at this point. Once you know the voltage, then we can easily find the current through each branch and the phase of the current. Okay, so we're going to go to the next page now and find the amplitude of that voltage and this additional phase factor right here. All right, so we're going to write a couple of equations now. If you think about V2, well, let's look at V2. All of these vectors I can break down into components. And I know that if I add the x components, they have to be equal to each other. And if I add the y components, they have to be equal to each other. So what we could say is like in the x direction, what do we have? In the x direction, you have to have that VR1 plus V2 cosine of phi 2. That has to be equal to V0 cosine of phi. Okay? You should be able to see that. We're going to call that for the equation in the x direction. In the vertical direction, again, there is no component of VR1 in that vertical direction. So this one's a lot easier, right? You have to have that V2 sine of phi 2 must be equal to V0 sine of phi. Okay, so that's pretty straightforward. The next thing we do now is we solve these equations. Right? Right away, since we know, remember, we know what V0 is, we know what phi is, so really you know a lot of these terms over here. What we can do first is get an expression for the angle phi 2. Okay, so what we're going to do now is simply use x equation. Let's rewrite in x direction. We'll just get this one by itself. Cosine of phi 2, you bring VR1 on the other side. Again, we know all these guys, so it's not too complicated. And in y direction, we're just going to leave that one the way it is, and you'll see why in a second. I hope you're having as much fun as I am today. Okay, now in order to get phi by itself, what you can do is take y divided by, take equation y and you divide it by equation x. So what that does, it's going to eliminate this amplitude V2, and you're going to be left with tangent of phi 2. That's convenient. And on this side, now you have to be a little bit careful. Sine of phi, then divided by a more complicated denominator term that has two terms. But these are just numbers at the end of the day. We're not trying to do everything algebraically. Okay, and if I go ahead now and I substitute in all the values, what I'm going to get is that the angle phi 2, again, looking at this diagram, I probably should get a negative value. And lo and behold, I do. I get minus 75.15 for this angle. Once you know the angle, you can just go back into this first equation over here and find what is the amplitude V2 for that voltage. You go ahead and do that. So you get that the voltage V2 is V0 sine of phi divided by sine of phi 2. And that gives me a magnitude of approximately 40.62 volts. Maybe off on the hundredths of a volt, depending on how I did my rounding and stuff, but gets me somewhere close enough. Okay, so now we have the voltage at that point in the circuit. All we have to do now is just find those last values of the currents through each branch, through the capacitor and through the resistor R2, and then find if there's any phase between the currents in those branches. All right, so we just simply now have to look at how do we calculate the current through, the current through the capacitor and the current in the branch with the resistance R2. Again, R2 was 100, capacitance was 100 microfarad. It's easiest to do the resistance R2 first, right? Because you know that the voltage has to be simply the value of the resistance multiplied by the current flowing in this branch, and that's simply this guy. But you know that, well, again, all we're looking for is what is this magnitude of the current. So it's the voltage, which is V2. It's this whole expression here, right? It has the same angular frequency. It has to have the same phase as that voltage, right? And then that gets divided by the value of the resistance R2. So this guy here is simply the amplitude, right? And right away, you should be able to see that this amplitude, let me just go ahead and write it. Write everything out here, R2 of T. So this is the voltage divided by the value of the resistance, which was 100. So this becomes 0.4062. We still have cos of omega t, and it's the same phase angle, right? Minus 75.15 degrees. So now we know the current flowing in that resistance R2, okay? It has to be in phase with the voltage over here. All we're left with now is this capacitor branch. All right, so for the capacitance, all you have to do, remember that V2 of t is simply equal to the voltage across that capacitance as a function of time. Okay, again, that you would write, we know the amplitude, we know the phase of the voltage. Now, the way you find the amplitude of the current in this branch is simply by applying Ohm's law to that one, okay? Again, you would write that the voltage across this capacitance, the amplitude, is related to the current, okay, by using the value of the reactance of that capacitor, okay? And that's it, okay? The reactance of the capacitor is 1 over omega c. So I would simply write this as 1 over omega c multiply by the magnitude of that current. So now we can calculate what this is. IC is going to be that voltage V2, that's VC, that's this amplitude. Again, it ends up being multiplied by omega c in this case. All right, if I bring this in the numerator side. So we get V2 was 40.62. What else? Capacitance was 100 microfarad, 10 to the minus 6. And we still had our omega, which was 377. Okay, so I get a magnitude of a current that has to be equal to roughly 1.53 amps. Okay, now the last thing you have to do is simply find what the phase angle is. Okay, so one thing you simply have to remember for capacitors here is for a capacitor or a branch that only has a capacitance like this, that the voltage lags the current. Or if you wanted to write it in terms of the current, you could say that the current leads the voltage and it always leads it by 90 degrees if it's only a capacitor here. Okay, so what would that mean if I try to write this second expression here as an equation? I know what the voltage is. This has to be the voltage, right? It's my V2 expression. So the way that you would write the current for this capacitor, you would write it as the magnitude. You would write it as cos of omega t. Okay, I'm going to just write phi 2, and at the end I'm going to introduce another angle because the current has to lead the voltage by 90 degrees. How do you make something lead? You add 90 degrees to it. Okay, if I add 90 degrees to it, it's going to lead the voltage by 90 degrees. Now remember, this guy was minus 75.15 degrees. So at the end, I can simply write that the current in the capacitor branch is IC, the magnitude, cos of omega t. And now if you simply combine both of those angles together, what you're going to get here is a positive angle plus 14.85 degrees. So the last thing I want to do now is I want to go back to my phasor diagram and I want to verify the junction rule right here at this point. Because what we have is a current, is green current I of t going in, and then I have the current through the capacitor, and I also have the current through the resistor R2 over here. Let's plot these on a phasor diagram to make sure that all these values here make sense on a phasor diagram. All right, the last thing I want to do now is simply check some of these values here for currents on a phasor diagram. Okay, so the way we do that is I'm just going to first plot I of t on a phasor diagram. It has no phase angle, right? The angle is 0. So the length of this vector here, 1 second, is going to be simply the magnitude. Okay, so this is 1.584. And all you do is you simply plot it along the x-axis because there's no phase angle. So let me go ahead and just write down this value, 1.584. All right, next thing you do now is, well, let's go ahead and plot IC. What would that one look like? IC has a slightly shorter length. However, it's not directed right there. It has a phase angle of 14.85, and that's a positive phase angle. So I kind of have to do something like this. Let's make this angle looks a little bit bigger than 14.85, but let me go ahead and plot that angle right here. This is 14.85, and the magnitude of this is 1.53 amps. Now you see what we're left with now. What we're left with here is this current IR2, right? And IR2 simply goes like this. Again, now you could plot it down over here. It doesn't matter where you plot it. I'm just going to put it at the end of IC. But again, the phase angle is minus 75, so it has to be somewhere down here. And actually, if I was going to move it, and I did things just correctly, it would look exactly like this, okay? So first of all, imagine you draw a small coordinate system here, just so we can define the angle. The angle is always defined relative to that positive x-axis. So imagine here, this is how you would define this angle. This here's the angle, minus 75.15 degrees. And the magnitude of this guy is simply 0.4062 amps. Okay? Now, does this make sense? So what does it say? It says that whatever current, if I add the current IT, right? Imagine what the junction rule would be here, right? If I says whatever current flows into the junction has to be the current flowing out. So that would look like I of t must be equal to the current going in the capacitor branch plus the current of going through that resistance R2. However, there are different phase angles. So that's why we use this phasor representation, and that's exactly what we have. This is IC. And this second vector, this shorter one, is IR2. And if I sum those up correctly with the correct phase values, I am going to get what the current I is. Okay? And that is the phasor representation of these currents right here. All right, so we solved everything, right? We found the current in every single branch. We found the voltage across every element in the circuit. There are different ways to do this. I kind of did it one approach, introduced some phasors in order to get the amplitudes and the phase values. It's nice to draw these things on these phasor diagrams and make sure that all the angles kind of work out at the end. Anyway, thanks for watching. If you have any questions, leave them in the comments section. I'll do my best to get back to you. All right, thanks for watching, folks.